Let's do some examples of trigonometric equations that have multiple trig functions involved. And we're going to solve between 0 and 2 pi, not including 2 pi. Let's say we have 2 cosine squared theta plus cosine of theta minus 1. And this is going to be set to 0. So because it's set to 0, I should probably factor out that left side, so I can set each factor to 0. And if you notice, it's actually in a quadratic form, because I have a term that's being squared, a term that's not being squared, and then a number. So I think this is going to factor, just like you would normally factor a trinomial. So if I want to get 2, it's got to be 2 times 1. If I want to get cosine squared, it's got to be cosine times cosine. That's 2 cosine squared. And then if I want to get a 1, product of 1 has got to be 1 and 1. To get a negative 1, 1 has to be plus, 1 has to be minus. So let's FOIL this back out. So 2 cosine theta, and then a cosine theta. So if I want positive cosine theta, I need 2 minus 1. Okay, so 2 cosine squared theta plus 2 cosine theta minus cosine theta minus 1, it checks. Okay, so now that it's factored, I'm going to set each factor to 0. And then solve each equation. So getting cosine of theta by itself, the first one gives me a 1/2. The second one gives me a negative 1. So I'm looking at a unit circle where the x-coordinate is 1/2 or negative 1. Okay, so looking for where the x-coordinate is 1/2 or negative 1. Okay, so where x is 1/2 is in the first and the fourth quadrant, taking place at pi over 3, and then at 5 pi over 3. And then where x is negative 1 would take place at pi, so we end up with 3 answers of pi over 3, pi, and 5 pi over 3. Let's try another one. Let's say we have the cosine squared theta minus sine squared theta plus sine theta. And again, this is equal to 0. So that's my first giveaway that I should probably factor the left side. But this one's not as straightforward as part A, because in part A, all the trig functions were the same. We had a cosine squared and we had a cosine. In this one, we have a sine squared and a sine, but then we have this cosine squared that's kind of throwing everything off. So I'm thinking in my head, something that involves cosine squared and sine squared is one of our Pythagorean identities. So one of our popular Pythagorean identities in trigonometry is that sine squared of theta plus cosine squared of theta equals 1. So I'm going to replace this cosine squared of theta with 1 minus sine squared of theta. So I'm just going to do a little substitution here. So that gives me 1 minus sine squared theta minus another sine squared theta plus sine theta equals 0. So now everything is in terms of sine. So I'm going to clean this up, and then we can probably factor it just like we did in part A. So I have minus 2 sine squared theta plus sine theta plus 1. I don't know about you, but I don't like negatives on my leading term here, so I'm going to divide everything by the negative. Looks better to me. So now I'm going to factor it just like I did in part A. So to get a 2, it's got to be 2 times 1. To get sine squared, it's got to be sine times sine. To get a product of 1, it's got to be 1 and 1. To get negative sine theta in the middle, this 2 sine theta has to be multiplied by the negative. So it becomes negative 2 sine theta plus sine theta. Okay, so now that I have it factored, I'm going to set each factor to 0. And then solve for sine of theta. Okay, so sine of theta is negative 1/2, or the sine of theta is 1. So since we're talking about sine, we're looking for the y-coordinate. So I'm looking for a y-coordinate of -1/2 or a y-coordinate of 1. So where y is a -1/2 is in the 3rd and 4th quadrants at 7 pi over 6 and 11 pi over 6. And then where the y-coordinate is 1 is at the top, which is at pi over 2. So we have 3 answers for theta: pi over 2, 7 pi over 6, and 11 pi over 6.